So let's take a look at this binary addition problem and really look at it in depth. So first, let's bring it into base 10 and see kind of what to expect. So we do the conversion here. We've got 8 plus 4, so 12, 13. Right? This number is 13. And here we've got 4 and a 1, so that's 5. And we add these guys together, and we end up with 18. And of course, remember that even in base 10, we do have some of these kind of hidden carries here. I guess it's not hidden, it's just we don't think about it in this case because our carry is 0, right? 5 plus 3 can fit into a single digit, so we don't have a carry. So the carries turn out to be very important when we think about overflow. So let's look at the binary case. So first let's do our math. And now here's the thing. Remember that we also usually make our adders to have a carry in as well. Right? So a carry in from another operation perhaps. So we're going to say that our carry in is 0. And so we got 0 plus a 1 plus a 1. So that is a 0 with a carry of a 1. And now we've got 1 plus 2 zeros, which is a 1. And of course we have a carry of a 0. It's a good idea to get in this behavior when you're adding binary to have your carries come out, or even if they're zeros or ones, to always show them. And now we got a 0 plus 2 ones, and that turns out to be a 0 with a carry of a 1. And now we've got 2 ones added together, so that's a 0 with a carry out of a 1. And let's do something to distinguish this right here, right? So we're going to drop this down, and there's that 1. So if this system were to be constrained in 4 bits, we only could deal with 4 bits. So maybe it's a 4-bit operating system. So there are special ways that we can get more than 4-bit number calculations, but for the most part, we usually stick within the bit width of our operating system. And so here, this is our 4-bit sum, and then of course this is our carry out. And so if we were to just look at the sum, our 4-bit sum that we're limited to 4 bits, our sum would only be 2, right? This is just 2, which is not correct, right? This is not 18. And just real quick, let's see what this actually is. We've got 16 plus 2, which is 18. So we did do our math right. But back to the 4-bit idea. This is not right, and what's happened is an overflow, right? If we look at the whole number, right, including this carry out, it is correct. But perhaps we have to save our sum somewhere, and we've designed everything around 4 bits. We wouldn't be able to save this 5th bit. So that's when we report an overflow. And how do we know if there is an overflow? Well, what we have to do is always, no surprise, pay attention to this carry here. This carry, or the C out, or in this case, each carry, each column of addition has a carry number associated with it. So, for example, this is C0, this is C1, C2, C3, and C4. So this is a 4-bit sequence, so we'll say in this case n equals 4. It's just 4 bits, n equals 4. So our rule for detecting if there's an overflow is if Cn equals, well, first let's say the case of 0. If it equals a 0, if this were to turn out to equal a 0, that would mean that everything was inside the 4 bits. And if it was inside just the 4 bits, that would mean that there is no overflow. So we'll say no overflow. And if Cn equals 1, in our case, that means that there is an overflow. So this is maybe something like this carry out would hook to an LED or something, and it would turn on saying there was an overflow. And we know that there was maybe an error that we have to address in some way, shape, or form. So this happens when we're adding two unsigned integer values. We can have overflow, and this is the way it works. We'll see that in some number systems this might work a little differently. But for right now, for unsigned binary addition, this is kind of our rule to detect an overflow.